Let's apply the z-score formula and gain a better understanding of z-scores. So why do we need z-scores? Let me use an example that illustrates how raw scores don't tell us very much, but we can learn a lot from those raw scores if we have some useful measures to compare them to. So we have this measure. It's a measure of attractiveness. And 3 guys take this test. Shifty scores a 35. Mickey scores a 65. And Antonio scores 90. What do these scores tell us? Just looking at the raw scores, we know that Antonio has a higher score than Shifty, so he's probably more attractive. Now that's assuming that this test is in an ascending order where higher scores mean more attractive. We don't know that for sure. We're just making a guess, making an assumption about that. We know that Shifty is lower than both Mickey and Antonio, and we can figure out how many points lower, but what do those points really mean? Maybe if we had the range for this test, if we knew that this test ran from 1 to 100, now those raw scores start to make a little more sense. If the scores ranged from, let's say, 25 to 150, the scores still make more sense, and we can understand that Antonio, instead of being 90 out of 100, now he's 90 out of 150. So his scores mean a little different when we know the range. But there's one other measure that can tell us a lot about these scores, and that is the mean. The mean of this test is the measure of the average performance. And if we know that the mean is 60, now we can tell quite a bit more about these scores. The first thing that we can do is see how far our raw scores fall from the mean. We can compute deviation scores. The formula for a deviation score is simply x minus the mean, where x is the raw score. So let's start with Shifty. His x score is 35. The mean is 60, which means that he has a deviation of negative 25. That means that he's 25 points below the mean. Mickey has a score of 65. That's just above the mean. If we take 65 minus 60, Mickey has a deviation score of positive 5. And Antonio has a deviation score of positive 30. That's 90 minus 60. But the question remains, how large are these deviations? We know how far the raw scores are from the mean, but we need something else. What we need is a standard by which to compare each deviation score. We need a standard deviation. And good news, we do have a measure, and it's called standard deviation. So we are going to use that standard deviation in order to make these numbers, these raw scores, more comparable and find out how far they fall relative to everybody else who's taken the test. So just like the mean is an average of all the scores in the sample, where we add up all the scores and divide by n, standard deviation is the average amount of deviation of all the scores in the samples. It's kind of like adding up all the deviation scores and dividing by n, except it's not quite that simple because the mean average deviation doesn't work. Remember, the mean average deviation always adds up to 0. But the standard deviation formula allows us to square the values, then add them up, then divide by n, and then unsquare them. Now we have a measure of the average amount of deviation, the average amount of variability in our sample. So let's apply this. We find out that the standard deviation of our test is 10. So the mean is 60, the standard deviation is 10. Here's what we can do. Take each of those deviation scores from the 3 guys, subtract their score from the mean, and then divide it by 10. What this will give us is a z-score. So Shifty had a score of 35. We subtract that from the mean of 60. It gives us a deviation score of negative 25. Divide that negative 25 by 10, and we get a z-score of negative 2.5. Do that for each of the remaining scores, and here's what we get. Shifty has a z-score of negative 2.50. Mickey has a z-score of 0.50. And Antonio has a z-score of positive 3.00. Now we know a lot about these deviation scores. In fact, we can put them into a z-distribution and see roughly where they fall. So Shifty, with his score of a negative 2.5, would be way down here on the low end of the curve. Mickey, with a positive 0.50, would be right there, and Antonio would be here on the far end of the curve. Now we can look at that z-distribution and we can get a sense for where these scores fall in relation to other people. Of all of the population of men who have taken this test, we can see that Shifty is way down in the lower end of the bell curve. There's not many guys lower than him. Mickey is right around average, just slightly higher than average. And Antonio is far above average. There's not too many guys more attractive than him. Most guys are less attractive than him. Because that purple line in this z-distribution represents probability, we can actually apply what we know about the distribution in a normal curve to these z-scores, and we can figure out precisely how many men are greater than or less than each of these three guys in their scores. So Shifty has a z-score of negative 2.50. It's way down on the low end of the bell curve. This comes out to a score that is actually greater than only 0.62% of all men. That means that it's less than 1% of guys who are lower than Shifty's score. For Mickey, he's slightly above average. His score is a positive 0.50. This is more attractive than 69.15% of all men. If you were to draw a line from Mickey's score straight up to the purple line that represents the normal distribution and see how many scores are below that, we know that half of the scores are below the mean, 0.50, and there's a small sliver that are above the mean all the way up to 0.50, where Mickey is. So we can use those numbers, add them together, and figure out that his score is higher than 69.15% of all men, or 69.15% of the rest of that curve. Finally, Antonio, far up in the top end of the bell curve, more attractive than 98.87% of all men. So, here's the question. Where do we get these numbers? Where do they come from? Where are these probabilities originating from? Well, the probabilities, or the source for those percentages, comes from a z-table. And that is what we're going to look at next.